Hi there. If you are watching this video, it's because you are struggling to learn how to balance reactions. Now, if you're watching this video, you should have already previously taken these notes at the top here of the page. This is, by the way, in your booklet. I'm going to be using, as examples to teach you a new method, I'm going to be using page 18. So these notes at the top you should already have if you're watching this video, and you're watching this video because you need a little bit of extra help, and that's fine. Remember that the basic idea with balancing reactions is that you have a number in front here that's called a coefficient, and it multiplies times all of the numbers down here. Those are called subscripts. Whatever number is in front, your coefficient multiplies times the subscript to tell you how many of an element there is present. So for instance, right now, if I write no number in front, we can assume that there are ones in these blanks. So a 1 times 8 would be 8 sulfurs, a 1 times 2 would be 2 oxygens. Over here, the coefficient when multiplied times the sulfur and times the oxygen. There's no number next to the sulfur, so we're going to assume it's just a 1. And for the subscript of oxygen, they've written it in 3. So 1 times 1 is 1 sulfur, 1 times 3 is 3 oxygens. Now previously, your teacher has probably taught you some sort of method like this where you write down for each element how many is present in the reaction if there's only one of each coefficient. And then your teacher has probably done something to say like, well, if these two numbers are not equal, you got to multiply them by something to make them equal. So over here, 1 times 8 would get us to equal 8. This number we're multiplying is what would be the coefficient that goes here. When we put this 8 here, it distributes not only to the sulfur and to the oxygen. So the oxygen is also times that 8, making 24 oxygens on this side now. Now our left side oxygen, there's still only 2 versus the 24 that we now have on the right. So we have to find something to multiply these 2 by to get it to equal 24, and 2 times 12 will equal 24. So this 12 is going to be a coefficient that goes in here. And now, when I've multiplied by 8 on this side to make 8 sulfurs on each side, the sulfurs are all equal. Multiplying by 8 on the right side has also changed my number of oxygens to be 24. So to get 24 on the left side, we had to multiply 2 times 12, and that 12 is what went in the blank. Now again, if you're watching this video, then probably you find this method confusing, and we need to find a different method that helps you understand balancing better. So for the rest of this video, I'm not going to do it this way. I'm going to do something different. This other method is slower than what I just did up here, but it is, I think, for most people less confusing, and it does work every time. So what we're going to do instead is we're going to try drawing each thing in the spot where the element or compound is. So right here, there's only 1 iron. We're going to draw ourselves, here's 1 iron. Right here, there are 2 oxygens. We're going to draw ourselves 1, 2 oxygens. On the right side, I have 2 irons, and I have 3 oxygens. So I'm going to draw each one. Now I can look at each element on the left side versus the right side. And I can see over here there's 1 iron, over here there's 2 irons. If I want to have a second iron over here to match this, then I have to find something to multiply times this 1 so that it'll equal the 2 that are on this side. So if I put a 2 here, this 2 multiplies times that iron. Now I don't have just 1 iron, now I have 2 times 1 I have a second iron now. But the only way I get this second iron is by writing a coefficient in this blank. If there's no coefficient here, I don't have a second iron to go here, and my 2 irons on the left and my irons on the right are not going to match up. But by putting this 2 here, it multiplies out to give me 2 irons over here to match the 2 irons on the product side. Let's take a look at the oxygens. On one side I have 2 oxygens, on another side I have 3 oxygens. When this happens, there's no whole number that I can do times 2 to make it equal to 3, and there's no whole number I can do times 3 to make it equal to 2. So I'm going to have to make both numbers of oxygens go up to a higher number. And when I do that, I'm going to end up trying to find the least common multiple. And the smallest number that both 2 and 3 can multiply into is 6. So you'll actually see this a lot where you have 2 of something on one side and 3 of something on the other side. And when that happens, you're always going to need to get them up to 6. So for instance, to get there to be 6 oxygens over here, if I multiply this side times 2, that 2 is times this 3. Now, instead of 1, 2, 3 oxygens, I have 2 times 3 oxygens. That makes 6. Over on this side, if I want to get up to 6, I need something times 2 that'll equal 6 like we had over here. So if I do 3 times 2, that makes 6 oxygens. Now, I have the same number of oxygens on both sides when I multiplied by 3 on one side and by 2 on the other side. At this point, you may notice that when we put this 2 here, that did change the oxygen, but that also changed to this iron. It distributes to the iron as well. So now there are no longer just 2 irons here. Now there's 2 times 2. That's 4 irons. Whereas on our reactant side, there are still only 2 irons. So to get to 4 here, I'm going to have to change this coefficient that we had written in earlier. I was doing 2 times 1 to get to 2. Now I need to get to 4. So instead of 2 times 1 equals 2, I need to change this to be 4 times 1. That will equal 4. The idea is still the same, that I have to put some number in this blank to change my amount of each element. And when I put a number in this blank, a coefficient, it will multiply. That idea stays the same even from this other method here, because that is what balancing is you have to put a number in the blank to multiply. It will multiply. You have to put numbers in there. If you don't put a number in there, then we assume it's just a 1 and it's not changing anything. Let's try another problem. For H2O, H2, and O2 here, I've got 2 H's and 1 O. I have 2 H's here. I have 2 O's here. I can see right now that my H's are already equal to each other, which is great. I have 1, 2 H's and 1, 2 H's, but my O's are not. There's 2 O's on the product side, there's 1 O on the reactant side. So I have to find this one where the number is lower, and I have to multiply it by something to get it to equal what's on this side on the right. So I have to take this 1 and multiply it by something until it equals 2. Well, 1 times 2. That'll distribute to the oxygen and give me a second oxygen. And now, my oxygens on the reactant side and on the product side are equal. The thing you have to look out for is that this 2 also distributes to the hydrogen. Now there are no longer just 2 hydrogens. Having a coefficient of 2 means that this 2 and this 2 get multiplied. 2 times 2 is 4, and you end up with 4 hydrogens here. And these 4 hydrogens don't match the 2 hydrogens that are on the product side. So if you want them to match, you're going to have to also put a coefficient here to multiply times this 2 to get it up to 4. So something times 2 needs to equal 4 like what we have on this side. If I do 2 times 2, then I can get to 4 hydrogens. And then all my hydrogens on the left side and the right side match as well. Let's try this for a more complicated problem. If we skip ahead a little bit to a double replacement problem on the next page, I want to do this one on the bottom. Now, a thing to look out for is anytime there's an ion from your chart at the back of your book. If there's an ion from your chart at the back of your book, you can draw that as a piece, a chunk together. So when we draw these, we have 1 iron and 3 chlorines. There are 3 beryllium here. And then these PO4s, that's called phosphate, those stay together as one chunk. PO4 is all one family, and we're not going to separate the family. So it says there are 2 of the family. We put 2 of them there. On the product side, 1 beryllium and 2 chlorines, 1 iron, and 1 phosphate. So we look for things that are easy to fix. And I'll go ahead and tell you right now, usually if you see this 2 and 3 situation, that's going to have to be fixed the same way over and over most of the time. So just like what we did over here, we saw that there was 2 oxygens on one side and 3 on the other side. So we multiplied to get them both up to 6. We switched it, 2 times 3 here, 3 times 2 there. That same situation is coming up again in this problem. It comes up over and over again. So on this side where I have 3, I can go ahead right now and multiply that by 2. On the side where I have 2, I can go ahead right now and multiply it by 3, because I know I'm going to have to get both of these up to 6 to make them equal. So this 2 times 3 does give me 6 chlorines. This 3 times 2 does give me 6 chlorines. And now all my chlorines are equal. But what you have to look out for is that that 2 coefficient here and this 3 coefficient here distribute. So this 2 is also times the iron, now there's a second iron. This 3 is also times the beryllium, now there are 3 beryllium. That actually is helpful in one case where right here that actually made my berylliums even out. But if I look at my irons, they don't match. If I look at my phosphates, they don't match. So let's pick one of them and fix it. I have 2 irons here and only 1 on the product side. So if I change this to be 2 here, that'll distribute to my iron and make a second iron here. And that, oh so conveniently, actually does make my irons match on the left side and on the right side. Now I have 2 on both sides. If I look at my phosphates, oh wait a second, now that's interesting. This 2 also distributes to the phosphate, making a second phosphate here. And oh my, that means I have 2 phosphates on this side to match the 2 phosphates that are on this side. So everything actually ended up evening out at this point. And I have no number written in this blank. That means we can leave a blank if we want, or we can write a 1. But the 1 will be implied even if we don't write it. I think that this method might just help with visualization a little bit. I'll do one more with you if you want to move to the combustion page. Now I said earlier this method will take longer, and that is going to be especially true on a combustion problem. But we can do it. 4 carbons, 8 hydrogens, 2 oxygens, 1 carbon, 2 oxygens, 2 hydrogens, 1 oxygen. Now with a combustion problem in particular, you should always do them in what I call CHO order. If we look, we know it's a combustion because we have CHO right here. There's a CH compound and O2. So I call these combustion problems CHO problems. And whenever we see a CHO problem, we know to do the elements in that order also. So fix your carbons, then your hydrogens, then your oxygens. So if we start with carbon, I have 1, 2, 3, 4 carbons here versus just 1 on this side. So I need to take this 1 and multiply it by something until it equals the 4 that's over here. So if I do times 4 on this carbon, that's going to make 1, 2, 3, 4 carbons here now. And that's going to match the other side. I'll also notice that this 4 distributes to the oxygen. 4 times 2 makes 8 oxygen now, which changes things, but we're going to do oxygen last anyway, so we're just going to hold off on touching that. We check off our carbon. We did the carbon. Next in CHO order is H. So I count 1, 2, 3, 4, 5, 6, 7, 8 on this side, and only 2 on this side. So I need something times this 2 to get it to equal the 8 over here. So what times 2 will equal 8? It's going to be a 4. That 4 is going to distribute. 4 times 2 gets me 8. So now I have 8 hydrogens here, which again is convenient because that matches real nicely with the 8 on the other side. And this 4 also distributes to the oxygen. 1, 2, 3, 4. Which again is going to change things for my oxygen, but we do things in CHO order. So we have finished our H. Now we can take a look at the oxygens. Remember that all these oxygens that are on the right side get counted together versus the oxygens on the left side. So over here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 oxygens versus only 2 on the left side. So I need to get this 2 up to 12, which means I need something times these 2 to equal the 12 total that are on the product side. So what times 2 is going to equal 12? It's going to be a 6. And I distribute that 6 to give myself, should have made more space, there we go, 12 oxygens. And I can count it off: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All my oxygens are equal, all my hydrogens are equal, all my carbons are equal. I have balanced the equation. I have the same stuff on the left side total as what I have on the right side total. This is a balanced equation. And then again, I can go back to this blank here, and I can just stick a 1 in there if it bothers me. You could also just leave it blank. It's totally fine. A blank, having no number, no coefficient in the blank just implies a 1. So it's all worked out here now, and hopefully maybe this method can help you if you were struggling.